Hi everyone, my name is Masoud Fatollahy. I'm working as a senior engineering solution specialist focusing on virtualization and NFV solution for the customer. And here is my colleague.
Yeah, hi, my name is Fredrik Karlsson and I work together with Masoud. And as Masoud said, today's topic is predictable performance with Nova. And just to quickly set the scene, so Wind River's legacy is an embedded systems company. So we're deployed all over the world, from we're the only operating system to on Mars down to the Boeing aircraft to your radio base stations. And as our customers transitions from purpose-built devices to cloud, and you may be surprised, but wherever you go, everything is going to the cloud now. We're sort of taking what is important for those customers, which is low latency, high throughput, carrier grade, etc., putting that back into OpenStack and trying to make cloud work for these kind of use cases. And so that's why we're going to talk about what we've done with Nova, how we are implementing it, how we're using it so that we can actually use OpenStack in these use cases where low latency, high performance, high throughput, and carrier grade is important. So with that, Masoud, please get into the technical details.
Thank you, Fredrik. Today, as my colleague said, we are going to talk about performance and how we can get this performance we need for this critical solution that we have both Telecom and other companies that require a lot of performance at the same time low latency. So in order to do that, we need some background. So I'm going to the steps that happened in this OpenStack, which component we touch when we launching the VM, and then we are going to actually to step for configuration, how we can configure our OpenStack to get the best performance we need and have the actually low latency for those critical applications. In this case, it's going to be a lot of configuration option you have in order to actually set the right value for your CPU, memory, and so on. So this is the high-level view of actually booting instance. As you can see, the first thing you do is just loading the image to the glance. Then we create the Cinder volume for that image. Later on, we create the networking we need for the instance, and the scheduler going to actually find the right compute node, find the right host to launch that instance, and finally the host going to launch the instance and bring it out on the line. In order to do that, we need to do actually some assumption. This assumption is that to make it simple for us, just jump over a lot of work to do before getting to launching one instance. One of those is that we assume that the OpenStack is running, the infrastructure is up, you have configured your provider network, and you have configured the admin have configured the flavor you need for your instance, and at the same time the user has actually configured and added the key pair he needs for the instance. Then we assume also that we are going to actually use the compute node that's running KVM. There is a lot of steps that is the same if you use other hypervisor, but in this case we're just focusing on KVM and going through that case. Let's start. The first thing, as I said, is that actually created the glance image. In the top line, you can see the OpenStack CLI you're using to create that image. This is very actually the bare minimum option you need to actually add the image to the glance. Otherwise, you know that there's a lot of options you have to set the different properties for the image. But in this case, we actually in all the steps, I'm just taking the minimal commands and options you need to actually boot the image. What happens when you run this command is that the glance API get the request, that do some validation for that request, and then loads the file that you want to add to the glance. And this file can actually be loaded locally from the file. It can be get it from different location. You can just give the location you want to fetch it from, or you can actually do it from the Cinder volume, that you can create the image from the Cinder. As you can see in the In the command line, you specify the format, which format, this format you want to have. Can you have raw, you can have QCOW2, or there is other option that you can also use in this case. And in the end, we actually give it the name, and that name is just for maintenance, and we have a track of which image we are using, because otherwise you get a very, very big UID that you want to actually avoid. You don't know which image is dependent on your UID. So when Glance API is loaded, that one, you're going to actually store the file in the configured backend, depending on which backend you are using for your Glance. You're going to store the image there, the file there, and Glance registry going to calculate and store the metadata you need for that image. Finally, when it's done, you're going to return a new UID for that Glance image to the caller. The next step is that using that image and using the OpenStack command line to create the volume. In that case, we give the image, we give the type of volume we need and which size we need. And finally, also, we give it the name that make it easier for us to work with that volume. When we run this command, the Cinder API process the HTTP request that comes to it, and it actually going to also validate this command, this request, and forward it to the Cinder scheduler via an RPC call. The Cinder scheduler going to select a volume that actually is stored based on the volume type. So you take a look at the volume type and a lot of other factors that is not important here, but you check those and going to select the volume you need. Then forward the volume, Cinder volume via your RPC call to the Cinder volume. The Cinder volume going to actually communicate with the backend to allocate the storage space that it needs for the size that we specify there. Then downloads the image from the Glance via then another API calls and convert it to the raw if it's necessary. If it's not in the raw, you're going to actually convert it to the raw and copy the image data to the backend storage. So what storage you have, storage solution you have, you're going to actually copy it to that backend storage. Then you're going to return the UUID for your volume. Next step is to set up the networking. In order to do that, in this case, I'm using the port create CLI of the OpenStack. We specify which network I want to have this interface or this port on, and I specify the VNIC type we need to provide for the instance itself, and give it the name. This VNIC type can be normal in case of VTIO. It can be also direct in case of SRIOV or PCI-passthrough if you want to use that kind of NIC. There are some other options here, but I just focus on those two. But you have more option here to specify the type of the NIC you want to use. When we run in this, again, the Neutron server get the request, validate the request, and also going to allocate the port you need, and going to associate that port to the network that you specify. When it's done, and do some actually housekeeping to save the information in its database, and also return the API to the caller. Then now we have image in place, we have a volume in place, we have networking in place. The next step is actually creating the instance itself. In order to create the instance, I'm using the server create. This command can be very long. If you take a look at the log when you're using the Nova, take a look at the Nova log, the Nova boot command, you can see that this is very long. So here you have a lot of options to optimize, to add whatever you need to provide to the instance itself. But in this case, again, I just use the bare minimum, using the volume we created, using the flavor to give the resources for the instance, and using the key name, and specify the port ID I need for this instance. And finally, give it a name. That name is very good that you can also have a very easy way to find the instance in your database or in your logs. When we run in this command, the Nova API going to process the request, validate it, and forward it to the Nova Conductor via an RPC call. The Nova Conductor going to do some housekeeping and forward it request to the Nova scheduler. This is a scheduler actually that has a very big job to find the right host for your instance. So what Nova scheduler does is actually you're going to check the resources available for each of the available compute nodes. You're going to check the CPU, RAM, storage you need, the ephemeral storage or whatever you need, and you're going to actually check your requirement, for instance, in the image properties or flavor extra spec that you use to specify the resources you need. For example, how many CPU you need for your instance, how much RAM you need, do you need huge pages, how big that huge page you need to have, what kind of hypervisor type you want to have in your instance, or actually you can define what kind of CPU you want to have in your instance too, in this case. Then he's going to check, look up the host aggregate and availability zone. That means that he checked that there are some grouping compute node that is in some available zone, that instance should go to that zone or not. Later, you're going to check the scheduler hint. In this case, it matter of server group. I don't know if you are familiar with the server group. That means that you actually, if there is any server group, that require affinity or anti-affinity policy for the VM or for the instance that should be launched. If that instance is included that group, then you're going to actually take care of this policy setting. If it's affinity in the same compute node or host, or is anti-affinity, that should be in a different host. When it's done with those lookup and those check, then he find maybe some of the compute nodes that are actually suitable for this instance. Then you're going to actually vet it out those compute nodes or those hosts that is not actually suitable for this instance. So through those that he find that is suitable, you're going to use one algorithm that calls Weyer to find out which of those are the best to actually launch this instance on. So that Weyer it can be configured in a config file, depending of requirement for your application. You can actually set different Weyer that choose the best one. For one of the example is that maybe you don't want to have all the VMs launching in one computer. You want to actually spread the VM in the different computer. That Weyer can actually see how many VMs is running in each computer that launch this in the computer that is available or has less VM, or other way around. If you want to just have all your instances in the first compute node, then could go to the next and so on. Then when is actually selected the suitable host, then you're going to return back to the Nova Conductor. So the host is selected in this case. The next step is that the Nova Conductor going to set up, actually look up in your database to find that compute node that has this host. If in terms of KVM is simple because each host is the compute node itself. But if you are using VMware, one compute node can take care of a lot of hosts. So it's more complicated. In that case, here you just look up the database, find the compute node, and pass the request to that compute node via an RPC cast. Here is actually RPC cast. That means that you don't wait for the response. You just fire it off and don't care about it. The rest of the calls from here is actually asynchronous call that is happening here. So the last step is actually for the compute node to launch this VM or this instance. So what it goes, it's going to find out and allocate the resources you need to launch this instance in terms of CPU, PCI devices, and also going to check that if the CPU should be shared, not shared, how much RAM you need to have for your instance, allocate the RAM, allocate the disks you need, and and check make it ready for your instance. Then you're going to actually do the async network allocation by calling to the Neutron API to make sure that those ports are available. And also going to connect to the Cinder volume, create a connection to the Cinder volume, and also make sure that the volume is in place, volume storage is in place. When it's done, actually all the resources are allocated for the instance. Then he comes to the KVM. From here is just KVM. Those steps we have taken actually can be the same for most of the hypervisor, but from here is just KVM based. So what KVM does, it's going to actually create a directory for this instance and add an XML file which is generated from the instance configuration we have done earlier. Then he's going to check if you need any local storage in terms of temporary or ephemeral or swap. Then you're going to be created if you need it. Then you're going to pull the actual Neutron to check the networking that is in place for your instance. And finally, you're going to actually configure the networking you need for your instance to talk through the host out to the world. So you're going to configure your vSwitch, vHost, or whatever technology you are using to give the connectivity to your instance. Then you set up the firewall rules as is specified, which firewall rules you want to have, and going to actually call the bit to start the VM. But in that case, now we have actually VM up and running and ready to go. That was the step you need to take to launch one VM. Now, if we go further, now we want to see how we can configure the OpenStack to get the best performance off of it. So in this case, as you know, it's 4 different, actually the part you need to think about. The first is CPU, how the cache is accessed, how the cache is used by different VM. The second is memory, how the memory access is used and shared or allocated for the instance. The third one is networking, how the networking is set up for your VM. And the final is storage that we are not going to talk about it here because it's very big discussion and very big actually stuff that cannot fit in 30 minutes and going through that one. When it comes to the CPU, as you must, maybe you know that if you installing the default OpenStack, you're going to, by default, overcommit 16 times the CPU. That means that 16 VM can use actually 1 CPU in the host. Or that you can actually imagine how it can actually create a contention that and impact your performance in your application. So in case that we want to avoid this, is that we reduce or disable the CPU overcommitment. And in this case, we can dedicate the CPU for the instance that nobody can use it. Or if you are using the hyper-threading, you can use the CPU thread policy to make sure that those sibling cores is actually used by one VM as not shared between those. The next that can happen between the host and guest is that when we have two problems. There's one problem is the system management interrupt. That is the BIOS actually. When it decides to do some housekeeping or doing something, going to interrupt everything else. Do the housekeeping, then you go back. That's going to impact the performance and impact all the applications. So in this case, we need to do some tweak in the BIOS or select a better hardware that actually have control over this interruption. The second one is that the host itself and the kernel processes on thread going to use all the available CPUs to do the job and running the thread, running the process at once. What happened here actually is that the CPU that is used by the host can be also used by the guest. This we want to avoid. So in case to avoiding this, we're trying to dedicate a specific CPUs and actually isolate them just to be run for the host, and isolate the rest of the CPU to be free to be used by the VM. And the host just use those CPU that we pin it to use. There are some command in both flavor and also in the kernel itself that you can use an glance image to actually set this option in order to isolate these cores. The last one is the cache contention. That, as I say, if you have a lot of VMs trying to actually accessing the cache in the CPU in the host, so you're going to be contention between those VMs. In that case, going to actually be a lot of swapping the cache to the disk. So it's going to be a lot of access, and cache is not going to be enough for all the CPU access we need. So in this case, what we need to do is that if you are using hyperthreading, use the thread policy again here to set the policy for your hypervising. And there are some other cache allocation technology that coming up that is very useful in this case, that you can avoid this contention for accessing the cache. If you come now is some details about hyperthreading, I talk about this, how you can use in this case. You have three different thread policy to set. One is isolated. That means that you're going to actually isolate using one of the core of those two siblings, and the second one going to be actually isolated. Nobody can use it. So you just use one core, and the other one is not used in the host. As you know, when you're using hyperthreading, you actually get two cores for one physical CPU. In this case, you make sure that you use one of those, that the second one is not used by anyone. The second is required. That means that if to set this thread policy, you make sure that both of those sibling cores for your hyperthreading going to be used by same VM in the same host. So that means that makes sure that nobody is actually sharing those sibling cores with your application. And third one that is preferred in this case is if we're trying to get those two from the same sibling cores, but if it's not possible, it's not going to fail. You're going to get another core from other sibling cores. So it's going to actually affect your application anyhow in this case. So you should make sure that write it wisely, because you have just one pipeline in this case. So if you don't want to use one sibling core from one CPU host and another sibling core from another CPU host in the same VM, it's going to affect your application. Next is that if you don't use in hyperthreading and you want to actually go ahead and managing your vCPU in the VM, in this case you have a possibility to set it to dedicated. That means that you only use it, or you want to have it as a share that you can be shared between the VM, between the application. So in this case, to get the best performance, is recommended to set it dedicated, not using the shared. The next level of actually the detail that we can do is that we can provide this Numa, Numa nodes that we have in the host to the guests. That guests have a picture of both Numa. If you have two Numas in the host, you provide the virtual Numa to the guest, and guests have both Numa, and in this case can use those to access the actually memory of different Numa and put the cores he wants to each of the Numa, mapping from the host to each of the Numa nodes he needs in the guest. It's a little bit complicated, but it's very easy. You just put the Numa node, available Numa node you have in the host to the guest, and define which CPU of the host be in which actually Numa zone in your guest. And you can put your application and using both Numas of the host in this case. And the next is that you can also set it to these cores as a real-time cores. That means that you're going to actually, Libet going to pre-allocate and lock the memory for your CPUs and going to actually make sure that that memory is not swapped out for your CPU in the host. And also run those a set of CPUs as a real-time CPUs in the host. So make sure that when you're doing this, use the real-time mask that just mask out those CPU that you don't want to be the real-time. Otherwise, you're going to get problem in this case. So all of those going to be as a real-time. So you're going to be contented with each other in this case. So when we provide in Numa, we also need to provide the RAM for each of the Numa as we do it in the host. So in this case, you have a possibility to set the RAM you need to provide to each Numa zone in your VM. And also at the same time, you're going to actually define what size of actually the huge page size you need to have in your VM. In this case, you have a small, large, any 2 meg or 1G in this case. Our benchmark shows that the best huge page size is 2 meg for the guest. You don't need more than 2 meg. The next step that is important also is that thinking about the PCI. That means that if your NIC is in one Numa node in the host, but your VM is in the another Numa node of the host, then you need to pass the KPI here that actually going to increase your performance by 50%. So it's very important to make sure that your VM using the core from the same Numa node in the host that your PCI device is, and also if you are using vSwitch, make sure that vSwitch core is also in that Numa zone, not in the different Numa when you have in your VM, using the CPU from that one. Yes, in this case, actually, it's good that when you're using the NICs for getting the performance, we recommend that to use the 10G or higher for getting the best performance you want to get. I think I have just 2 more slides to go. When it comes to the guest, you can see that the type of the NIC we specify actually give you different performance. If you're using the emulated NICs like E1000, then you get very, very slow performance in this case. If you go to and using the paravirtualized NIC, right, VTIO, you get better performance, boosted your performance. If you're using the SRIOV or PCI-passthrough, you're going to be much faster because you get the real NIC in your guest. But you have some downsides with that is that you're going to miss the live migration, you're going to miss the security, you're going to miss all the feature that exists in your virtual switch because you're bypassing everything. So all of those should be taken care in the guest and in your top of the rack switch. It'll be a little bit harder to configure when you're using the SRIOV. We recommended actually to use the DPDK because we have benchmark this and see that DPDK is the fastest way to go. And in this case, you're using the pull mode driver and using the less core for your AVS in this case. But the downside is that you're going to draw more power because all the cores going to be in the loop all the time, pulling the data. That's the last slide. Just what we have done today, we have gone through the steps to launch the instance. We have actually see all the components are actually affected and is used when you're launching the VM, and we have actually say that we have a lot of options to work with to configure the OpenStack to get the best performance in this case and leverage all the options we can use through the Nova and using the both flavor or image, Gillen's image command to add those options we need. And also we have find in our communication with the customer that the performance and the latency are those 2 most important part for critical application. Thank you. With that, I'm open for question. I hope I'm not passing 30 minutes.
All good. All good.
All good? Yeah?
Questions?
Yeah?
Yeah, I somehow look at the network and the network, so for example, bandwidth capabilities when you schedule the VMs.
Network and? Sorry?
Are you looking for the bandwidth demands of the VMs when you schedule them? I mean, you spoke about latency and getting packets quickly to the VMs, and that also depends, on the overall network demands that the set of VMs have.
Yeah.
Are you looking into that? Are you using that?
Right now, I can say that, that the question was if I'm taking care of the bandwidth request for requirement for the VM, if we take care of those. Today, the way we are doing, we give the 10G NIC to the VM. It is actually depend on how application or company going to use that. We are not setting up any limitation or traffic shaping to have this control over the bandwidth for the VM.
So you give each VM 10 gig?
Depending of your VNIC type. If you're using the, Vitaio or E1000, you get different actually capacity. But if we have seen, if you're using DPDK, technology in the DPDK, in the guest, then you can get line rate. If you have 10G, so you can get 10G to the one NIC.
You normally don't have the number of times VM times 10 gig on your interface, right?
Yeah, but
You have to have some bandwidth sharing, and it's also not only about the bandwidth on the link. This also impacts the CPU of the host and the vSwitch and that. So that's why it's not just an over-provisioning issue.
Yeah, you have right. You should have some kind of traffic shaping in place that you can decide how much bandwidth you want to give to each application. That is actually possible if you use in the virtual switch. You have that possibility to set the bandwidth limitation for your application. We haven't actually done any benchmarking for bandwidth limitation, no. But you have that possibility in Nova OS. Yeah.
Wouldn't you agree that that's part of
Yeah, we have seen some interest about this. They ask us about this bandwidth, but this is actually the functionality you can put and enable in your virtual switch. In this case, if you want to use the virtual switch. Otherwise, it's going to be much harder using PCI-passthrough or SRIOV because you don't have any control over.
I understand that, but it's not only about what features you can enable, it's also about whether you can actually get the performance that you claim that you can get here without doing that.
What you're saying is that make sure that VM has that capacity that it requires, that is not less or higher that requirement, right? Yeah.
Ensuring that, and it's also a way of protecting the CPUs. It's not only about...
Yeah. That's correct. That's correct. Then you have actually protecting the CPU that you are using in your virtual switch that is not working. Yeah. But we haven't done any benchmarking on that one.
And you're not deploying it anymore?
No, we haven't.
Do you have any plans on that?
Yeah, I think, as I say, we get some requests. We have it in the roadmap, but it's not actually clear which release is going to have that in place. Yeah, thank you.
Any other? There's another question.
Yeah, have you noticed any performance increase when two VMs share the same node? Communication between each other?
Sharing the same node, that means that they are running in the same compute node. I don't see any decrease now. We have our benchmarking show that we don't have to get the line rate, depending on how many cores you are using your virtual switch.
Is there an increase between running them on separate compute nodes or the same?
The increase is actually depend on your top of the rack switch and the latency that goes to, because when you're passing from one compute node to another, you have to go to the top of the rack switch, going to the next compute node, going down. So that's latency, or that's if you have those in place. So I don't see any actually increases. So you get the best if they are in the same host, of course. But if you have in the different hosts, of course, you lose some performance, because if you have to go to the top of the rack switch, go to the next compute node. Yes?
I'm still a bit confused about the advantages of the PDK and actual
SRIOV?
not SRIOV specifically, but
Vitayo?
PDK is pulling a lot, and you're going to consume a lot of CPUs. So then you can also about to allocate more CPUs to the traffic itself than to the VM. So there's a kind of a loss trade-off there that you don't have when you use SRIOV or etc. So how do you, I mean, you said you recommend PDK, but how do you justify or how do you appreciate what is the most valuable in your deployment?
Yeah.
I mean, direct pass-through SRIOV to capabilities and or more CPU allocated to the network, and that has impacts on the VMs. And how do you make those trade-offs? What makes the recommendation?
Yeah, as I mentioned here earlier, that in order to use the PDK, you need to actually have a set of cores you need to get those line rate or the performance you need. But that is both in your virtual switch and your application. So if I want the PDK, use the PDK in my application, I'm going to allocate 2 cores just for forwarding, just for data, and 1 core just isolated for the management for the host. So those 2 cores that is for data is only used for the PDK. And 1 core that's keeping the host and do the host keeping in your application.
And it also, I mean, in our case, we do support all the way from the PDK down, but it all depends on what your KPIs are as well. I mean, for most of at least our customers, things like live migration and absolutely hitless upgrades, so of OpenStack and everything, it's an absolute must, because we're not talking 3 nines, we're talking 6 nines, or 100% is not really achievable, but yeah, we're talking those kind of uptimes. Critical applications. So if you want things like hitless upgrades and live migration and so on, then SRIOV is not going to cut it. Then, of course, it's a trade-off.
Not now, at least. But I think that there are some activity ongoing to make sure that we can do the live migration in SRIOV, but it's not done yet. Some work is ongoing.
So, yeah. It's about scaling, supporting all the different scenarios and then deciding what is important to you. And I mean, one thing that we see constantly is that some of our customers actually think that their application is more critical than they actually are. So, you need to do that sort of research as well. How critical is this? If it's life and death, if it's, your internal web pages, of course it's not. But if it's autonomous cars, for instance, then, yeah. You have different scenarios and different use cases. You just need to make sure that you scale all the way. Yeah. Because that's the use cases that we're actually seeing with fog and edge computing, is that, near life and death situations at least.
Yeah, it's critical, yeah, of course.
But as a cloud operator, how would you charge for this kind of things? How would you decide when you allocate your infrastructure? And how you would charge for the different models?
I mean, it's usually depending on some of our customers build private clouds, because they just expected to deliver on these sort of requirements. Other, when we're working together with the sort of more data center type of folks, it's because they want a premium SLA. For instance, for one use case that we have a lot is government and also aerospace defense, where the requirements maybe are higher on SLAs. So yeah, SLA is one way, but of course, it's a niche.
Any other question?
Well then, thank you very much.
Thank you very much. Thanks, guys.
Thank you for your time.
Thank you.